Hi, everyone. Welcome back. This is Earth and Space Science 101. We're still in Unit 1, so we're still discussing tectonics. And this time we're going to bring it around full circle and re-explore some of the things that we talked about in Lecture 1. Lecture 1 was our geology overview, where we first introduced the subject of plate tectonics, and we discussed the different types of plate boundaries. Today we're going to look at the history of the plate tectonics theory and some of the more modern approaches to plate tectonics. We're also going to discuss the subject of mountain building today and go on a little field trip involving some mountains, so it should be a lot of fun. Now, when we left off talking about plate tectonics, when we talked about it originally, I mentioned the father of the plate tectonics movement, Alfred Wegener. We're going to be talking about him a little bit more today and some of his triumphs and downfalls. So Alfred Wegener was a meteorologist. He was doing science in the early 20th century, and he was largely involved in doing things like exploring glaciers and looking at ice flows. Something pretty far outside the realm of geology. But he made what you could argue is one of the most important ideas. He came up with one of the most important theories in geology in sort of all of human history. He introduced this idea as continental drift, and this is something he proposed in 1912. So Wegener's support for the continental drift hypothesis was the puzzle-like fit of the continents, different patterns in rocks and ice flows and glacier patterns, and fossil distributions on non-adjacent continents. Basically, sort of places where you find fossils on different continents, but there's really sort of no understanding of how they could have gotten from one continent to another continent half a world away. So there's definitely some evidence for this continental drift idea, but he was lacking a driving mechanism. So we're going to find out in just a little while here that he didn't have a lot of support in the geological community, and during the whole of his lifetime, he didn't really have a lot of support for the continental drift hypothesis. So when we talked about plate tectonics back in Lecture 1, we introduced this idea of the continents all being arranged together as one large megacontinent, or the term we use is supercontinent. This is where all of the major continental land masses that are on Earth today and spread out around the globe are at one point in the Earth's past configured together as one big continent, one supercontinent. The most recent supercontinent is named Pangaea, and it was actually Wegener who coined this term and came up with this idea that at some point they had all been arranged together. And now, this puzzle-like fit of the continents that you can see anytime you look at a map and look at opposite sides of the Atlantic Ocean, you can easily see how those continents could fit together if the Atlantic Ocean wasn't between them. This was sort of the main piece of evidence behind his continental drift hypothesis. Anybody that had access to a map, anybody that could see the layout of the continents could see that they could actually fit together like puzzle pieces. So in this animation, you can see that this fit of the continents was then broken up by the formation of the Atlantic Ocean. It wedged apart the continents and pushed them apart. And then along the way, North and South America split apart. Other continental land masses sort of arranged themselves and moved themselves around the globe to the configuration that we see now. But at some point in the past, they were all arranged together as one big supercontinent. Now, this alone is not enough to actually prove to anyone that the continents did actually move, that they aren't just fixed, that geology isn't just static. And so this is why Wegener didn't really get a whole lot of support for his theory originally, with the lack of a driving mechanism. No matter how much evidence that you have behind it, it's still just not going to really work out very well. It's not going to be very well supported. Another big important line of evidence that I had discussed earlier on that very first slide was the fossil distributions that you see worldwide. Now, some of these fossils are a little bit more recent. They might be early Cenozoic to Mesozoic, making them anywhere from, let's say, like 50 to 100 million years old. Some of them are much older than that, 3 or 400 million years old. But all of the different fossils that you see laid out on this map are found on continents that are non-adjacent today, so they're not connected today. And so the only real thing that actually makes sense is that these continents were at some point fixed right next to each other. I want to pick on one fossil that's found on almost every major continental landmass today. And this is an organism that's, of course, extinct today and only found within these layers of rocks that have been dated to be on the order of 300 million years old. This fossil that I'm going to talk about today has a little leaf pattern on this map, and the name of this fossil is Glossopteris. So Glossopteris was a fern. It's basically gone at this point. It's basically extinct. But you can find the fossil evidence on South America, Africa, India, Antarctica, and Australia. All of these major land masses that are now separated by vast amounts of water today. So how did these seeds to start new organisms get from South America to Africa and Africa to Australia if there were oceans between these continents at the time when this organism was around? Like I said, it wasn't enough on its own to prove Wegener's continental drift hypothesis, but it's pretty compelling stuff, and it's certainly one answer. As we'll find out a little bit later, it ended up being the correct answer to all of the paleontologists' fossil problem at the time. Glacial patterns, lava flows also sort of match up with this. And this is some of the stuff that you're seeing on the very right-hand side of the image. Lava flows in northern South America and Africa, ice flows in the southern part of South America and Africa, all dating back to some point in time when those continents were still connected. So, like I said, we wouldn't be talking about him today if he wasn't actually right all along, but he was laughed off the world stage. The geologists of the era, but one, didn't really want to take the word of a mere meteorologist, somebody who didn't even work exclusively in their field. And two, they weren't very willing to even really hear him out because he couldn't explain why the continents were moving. And this is something that's very important, not just in geology, but in all sciences, that it doesn't only matter what the evidence is for this particular theory. You also have to be able to explain why some particular phenomena is occurring. In this case, why are the continents in motion? And that's something he could never really answer. You know, was it magic? Was it massive elephants pushing these continents around? What was the actual driving force? This would be something that we would not actually understand for another 50 years. This isn't something we would understand until we had a better idea of what the sea floor looks like. And then we'll be able to take a lot of the magic out of this and see that there are basic mechanics for why the continents are in motion that have to do with the creation and destruction of the ocean floor. So this driving force for continental drift that would later be called plate tectonics ended up being the creation and destruction of the ocean floor, the plate tectonic cycle. And the plate tectonic cycle, as we already know, is driven by mantle convection. Again, because the interior of the Earth is hot, it undergoes convection, heat rises. As heat rises, the plates drift apart. As the cold material sinks back down, that's typically where the plates themselves sink back down, subduct back down into the mantle, and are ultimately destroyed. So this is going to be really important as an overall driving force for plate tectonics. But you have to think back into the era of 1912 and Wegener's original hypothesis. We didn't have any idea of what the seafloor looked like. The seafloor was as unknown to us as the surface of the moon before the moon landings, even possibly more abstract to us. It would be, similar to trying to understand what's going on Neptune or some outer planet on the solar system. It was a completely unexplored environment. So as we flash forward another 50 years, we get into this era after World War II. And World War II ends up being a very important catalyst for lots of scientific discoveries. One of the most notable in geology being our understanding of the seafloor and how that helps prove plate tectonics. So in World War II, exquisite, very detailed maps of the ocean floor were created to advance the front of submarine warfare, including the first very, very detailed map of the Atlantic Ocean. Now, they thought what they were going to find upon mapping the Atlantic Ocean was essentially a lot of flat ocean floor, because the vast majority of the ocean floor is flat and almost completely lacking in any kind of relief, any kind of topography, anything really interesting happening. There's basically just a lot of flat nothingness on the ocean floor. It's part of the ocean floor that we refer to as the abyssal plain. What they actually ended up finding in the mapping that took place in World War II was all of this relief where they didn't really expect it to be. Right down the middle of the Atlantic Ocean, they found something that we now call today the Mid-Atlantic Ridge. This essentially underwater mountain range, a volcanic range that extends almost from the North Pole all the way down to the South Pole. The entirety of the Atlantic Ocean, all the way down the middle, you have this underwater mountain range. And it would later be determined that this is where the new crust is created in the Atlantic Ocean. This is part of the driving force that keeps the plate tectonic cycle going, is this mid-Atlantic ridge that is the divergent plate boundary, creating new crust and dividing the New World from the Old World, or North and South America from Europe and Africa. So it wouldn't be until after World War II, someone associated with the Navy in the United States military, a guy named Harry Hess, came up with this mechanism for Wegener's continental drift called seafloor spreading. And seafloor spreading basically is the same thing as this idea that at mid-Atlantic ridges, these plates are moving apart, new crust is creating itself at the mid-ocean ridge, and that these continents are drifting further and further and further apart. So again, the mid-ocean ridges taking at their location in the middle of the oceans, this is where all the new crust, the new oceanic crust is getting created. The destruction of the old crust, again, this is all almost exclusively oceanic crust, is taking place adjacent to continents and adjacent to other pieces of oceanic lithosphere crust. And this is going to be marked by trenches and volcanic islands at convergent plate boundaries. So again, a really important idea to kind of keep in mind here is that plate tectonics is all about the creation of the new and the destruction of the old. And this process, this cyclicity, keeps the continents just sort of moving along for the ride. They're almost sort of like a side effect of the recycling that happens in plate tectonics. So there are some lines of evidence for this plate tectonics theory that kind of help us to accept the plate tectonics theory, and it helps us to further understand it and to be able to reconstruct the position of the continents at various points in the Earth's past. One very important line of evidence is the age of the oceanic crust and how it varies with distance from the mid-ocean ridges where it's first created. So as you would expect, at the mid-ocean ridges, this is where the youngest crust exists, because this is the crust that has just been newly formed. All of this upwelling of hot material from the mantle, it's moving up to the surface, cooling, solidifying, and making new crust right here at this high point on the ocean floor, the underwater mountain range, or the mid-ocean ridge. With increasing distance from the mid-ocean ridges, as you get further and further and further away, you get into older and older and older and older crust. It's very similar to sort of like a double conveyor belt, where you have one point where the conveyor belts are meeting in the middle, and then they're spreading outwards from there. So if you could think of the age of the conveyor belt as being how long has that part of the conveyor belt been up on the surface, you would have older and older and older material as you moved further and further and further away, as that material sort of spent more and more time on the conveyor belt. So not only does the crust get older with increasing distance from the mid-ocean ridge, it also gets more dense, more compacted. The elevation of the seafloor gets lower. As you get out into the abyssal plain, that remains pretty uniform throughout the abyssal plain. And at the oldest oceanic crust, this is going to be the stuff that's going to be most susceptible to being subducted back into the mantle. So let's say you have two pieces of oceanic crust that then move towards each other. The older and denser of the two pieces of crust is going to be the one that subducts beneath the other. So this is a wonderful image to be able to sort of understand, one, where the mid-ocean ridges exist today, and two, this relationship between the age of the crust and the distance from the mid-ocean ridges. What you're seeing here is sort of a color-coded map of the age of the oceanic crust worldwide. So for once, we can basically completely ignore the continents. The continents are just along for the ride in this particular image. And so they're all colored in beige, and everything else is oceanic crust in this picture. The warmer colors, the red in this picture, is all of the newly created crust right up against the mid-ocean ridges. It's the stuff that was just formed and then moves outwards as the crust continues to form itself at these mid-ocean ridges. So obviously you have this mid-ocean ridge running right down the middle of the Atlantic. That's the mid-Atlantic ridge. It sort of splits apart in the South Atlantic, and you have two separate divergent plate boundaries there. You have separate divergent plate boundaries or mid-ocean ridges in the Indian Ocean, and then one major one in the Pacific. Another thing that you can take away from this image is that the rate of plate motion is not uniform worldwide. Plate motion is almost twice as fast in the Pacific as it is in the Atlantic. And you can tell this by the width of the red and the other color-coded bits of crust here. That's how much crust has been created in a particular amount of time. If you have more crust created in the same amount of time, that means a faster rate of plate motion. So as you move away from the reds and into the greens and blues, you get into progressively older and older and older crust. And worldwide, it turns out that there really is very, very little to almost no oceanic crust that's over 200 million years in age. 200 million years, again, sounds like a really, really long time to us. To the Earth, that's nothing. 200 million years is only a tiny fraction, less than 5% of the overall age of the Earth. So the continental crust can be billions of years old. It can be multiple billions of years old because the Earth itself is 4.5 billion years old. So 200 million years really gives you a pretty good idea of how quickly the oceanic crust regenerates itself, what a short lifespan that oceanic crust really has in the grand scheme of things. And then the continents just continue to move along for the ride. Now, another really important line of evidence for the plate tectonics theory is paleomagnetism, which is just a fancy way of saying old magnetism, the magnetism of rocks in the Earth's crust at various points throughout geologic time. So when the plate tectonics theory was still in this process of being accepted, we needed more and more evidence to be sure of the fact. Even though we call it the theory of plate tectonics today, compared to most things that you would assign the word theory to, it's essentially scientific fact, or many lines of evidence for the movement of the continents and the creation and destruction of the oceanic crust. So paleomagnetism is just one of these lines of evidence, and it relies on something that we talked about in the previous lecture, Lecture 4, on the Earth's interior. The interior of the Earth, the outer core to be specific, is in a molten state and composed of iron and nickel. And this iron and nickel, being in a liquid state and being very hot, is constantly undergoing convection. The movement of that outer core, that liquid iron and nickel, creates the Earth's magnetic field. And then that magnetic field helps keep these electric currents within the outer core going. It's a self-sustaining system. Now, that system occasionally reverses itself, as we also discussed in the last class period. The field weakens over time and then reasserts itself in the opposite direction of polarity. So right now, the north geographic pole is also in the same position as the north magnetic pole, or where all of the magnetic field lines run back into the Earth. At various points, it has run in the opposite direction. It's run north to south instead of south to north. We can see which rocks were created under what polarity, whether it's sort of normal like it is today or reversed, at various points on the ocean floor. And there's a mirror pattern in this magnetic signature on either side of mid-ocean ridges. And that's illustrated in the image that accompanies all of this information. You can see the kind of color-coded oceanic crust in this image. The black is representing the magnetic field in the polarity that it has today, and a normal polarity. And so for 713,000 years, the magnetic field has run in this same direction. That means that all of the crust that gets created as the magnetic field runs in this direction is going to have this particular direction of polarity. At some point, though, however, in the Earth's past, prior to 713,000 years, the magnetic field ran in the opposite direction. And the rocks that cooled and solidified under that magnetic field carry with it that signature of being in a reversed polarity. And then that reversed polarity then indicates to us that not only was the field running in the opposite direction, but these rocks created and now placed on opposite sides of the mid-ocean ridge were actually created at the ridge itself and then pushed outwards. So the application of paleomagnetism to the study of the Earth's plate tectonics cycle was first proposed by a team of geologists, Matthew and Vines. And this has become very seminal and very important work in helping to prove the plate tectonics cycle. Not only does this help prove plate tectonics, but we can use the direction of the polarity recorded in these rocks to give us an idea of where these tectonic plates were located at various points in the past. So take, for instance, we know where some part of the Atlantic Ocean is placed today, but we can trace it back through its history to where that plate was at various points in the past. So if we can do this, dating not just to hundreds of thousands of years ago, but to hundreds of millions of years ago, we can reconstruct what the Earth looked like at various points in the Earth's past. We can essentially prove that 250 million years ago, all of the continents were located as one big supercontinent. And the paleomagnetism helps us prove that. It helps solidify this idea of where exactly these tectonic plates were located at various points in the past. So all of this is very important. Not only are we at this point of being able to prove without a shred of the doubt that the plate tectonic cycle is something real and happening, even though it's not something that occurs in time frames that you and I can really start to understand, that we can tell that this has happened, that the Earth changes over time. We can go back and use it as a tool to recreate the Earth during various points in Earth history. And that's really powerful. That almost allows us to time travel. And this is all particularly mind-boggling because you have to remember that these plates are moving at the same rate in which your fingernails grow. So to be able to add up to a substantial enough amount of time to allow for one continent to move all the way around the Earth, that takes not thousands of years, but hundreds of millions of years to occur. So it takes a really long time for things to look particularly different, and it's a very sort of powerful idea that the Earth has actually changed this substantially throughout time. So now we're going to move away from the history of the plate tectonics theory to sort of modern plate tectonics and take another look at what actually drives plate tectonics. Is it so much the creation of the new or the destruction of the old? And this, becomes a little almost whimsical to think about because it's almost like a chicken and the egg scenario, what came first. But we're going to find out that all of these individual components are really important in driving plate tectonics. So we know already that mantle convection, that heat in the mantle and the redistribution of material in the mantle because of that heat, is the driving force for plate tectonics. But you can also think about plate tectonics as helping to drive convection in the mantle. So again, it's what came first, the chicken or the egg. We think about a cause and effect. Right, we think about something coming first and then something coming second. And so far, I've introduced this as you have heat in the mantle, that heat rises, all this molten material rises up to the surface, it pushes apart continents, and it creates new oceanic crust, and that sets off everything else in motion. But it's also this effect on the surface and the subduction of plates back down into the mantle that help keep these convective cells in the mantle going. In order to have a convective cycle in the mantle taking place and working over hundreds of millions of years, you do need something to keep it going, or there's really nothing to stop it from dying out and some new convective cell taking root somewhere else in the mantle. So mantle convection can be thought of as the cause or effect of the circulation set up by the pushing apart of the plates at the mid-ocean ridges, and then the pulling down of these slabs of this continental crust as it sinks back down into the mantle. So again, there's no right answer here. There's no what came first, the chicken or the egg. It's just something to think about. There's a cyclicity to it that is just as much affected by the motion of the plates as it is by mantle convection. And this cycle seems to be self-sustaining as long as there is enough heat to create a Earth's mantle that's hot enough to actually undergo convection and to have isolated points where there's magma in the mantle. So having these isolated points where there is magma in the mantle or rock, essentially just in a liquid state, is also very important for the plate tectonic cycle. Without having these convective cells meeting up at a certain point and allowing for a lot of heat to move upwards towards the surface, you don't really get any kind of substantial amount of plate movement occurring. So places where these convective cells meet and then this material moves upwards, these places are called mantle plumes. And sometimes they're quite small and they don't actively create plate boundaries. But often these mantle plumes are enormous. You have enough molten material in the mantle to surge all the way up towards the surface, to spread out on a line underneath the crust, and to actually melt and divide the crust above. That's a substantial amount of heat and a substantial amount of magma in the mantle that's making that possible. So when this occurs, we think of it as rifting the either continent or oceanic crust above. It rifts the plate above. So no matter where this is taking place, it can be somewhat arbitrary. If it's taking place under a continent or if it's taking place under the oceans, the plate, whatever happens to be above, is going to then split apart and new crust is going to fill in the gap. So sometimes this is underneath the continents. And this is how continents split apart. This is how the great supercontinent Pangaea split apart 250 million years ago. And then after that rifting occurs, the continents then drift apart on the trailing edges of these continents as they're forced apart. And then what's forcing them apart is the creation of all this new oceanic crust in the gap. And that new oceanic crust continues to recycle itself. It continues to solidify on the ocean floor. And by definition, because all of this material from the mantle is very dense, you can really only form oceanic crust here. You can't form more continent. And that's why divergent plate boundaries are always going to create specifically new oceanic crust and not new continental crust. It's because of what's coming up from below, what the makeup of the mantle is like. So you're not always going to have this rifting occur. You need a substantial amount of heat, a substantial amount of magma surging up towards the mantle to actually go through the business of rifting apart an entire continent and to continue the motion of that continent and to force them to continue to move apart. Smaller mantle plumes produce something called hotspots. And as the continents and the oceanic crust, as the lithosphere above, moves over these hot spots, you basically just have these isolated volcanic activity that's taking place. As that tectonic plate moves over the hot spot, you create some amount of geological material, some amount of heat, melting of the crust, some volcanic activity, and as that part of the plate moves away, then it's the source of all of that volcanic activity dies with it. And you have volcanic activity then popping up in a new place. So while most volcanic islands take place at subduction zones, so they are located actually on a plate boundary, you get these isolated volcanoes that can be completely independent of plate boundaries. And that's why we're calling them hotspots. You can basically think of all of the convergent plate boundaries as definitely being hotspots, whole hot lines. But to have these individual hotspots, you have to have these mantle plumes that are helping to feed that volcanic activity. So in the United States, we have two very well-known volcanoes that are located, that are going to be tied to these mantle hotspots. One is Yellowstone. So this is a hotspot that's located underneath the continent, and it's helping to produce all of this volcanic activity. As the North American plate continues to move, it will move so that the Yellowstone area will not be directly above that hotspot, and then it loses its steam. It doesn't have any ongoing volcanic activity. The other place, the second place where you have a lot of volcanic activity that's related to a mantle hotspot is the Hawaiian Islands today. So in Hawaii, you have several islands. You've got the big island of Hawaii, and then you have some of the smaller islands of Hawaii, like Maui and Molokai. As you move further and further off to the northwest, away from the big island of Hawaii, the islands tend to get smaller, and the amount of volcanic activity becomes increasingly less, and all of these islands become older and older and older. At some point, the Pacific Plate was located in such a way that it was actually that the hotspot was actually located under one of the smaller islands of Hawaii, and then that built up. That created a substantial amount of volcanic activity. You created this large volcano, and then as the plate continues to move over that hotspot, that volcano then eroded down. So when you look at the smaller islands of Hawaii, you're looking at essentially extinct volcanoes. And you're looking at something that, given a few more million years, will be gone. It will have been eroded back into the ocean because this particular type of rock is not very resistant to erosion like the continents are. Now, the big island of Hawaii is where the active hotspot is, and not located under the central part of the big island of Hawaii, but actually off to the southeast, where we had a lot of we recently had a lot of volcanic activity taking place. So what you're seeing there is the formation of the newest part of the Hawaiian island chain. And as the plate moves over that hotspot, you're essentially going to create more and more volcanic islands as part of the Hawaiian island chain. Now, if you go underneath the ocean and you look off to the northwest of the Hawaiian Islands, you can see that this hotspot has a long history beyond just the main Hawaiian Islands that we see today. There are basically submerged extinct volcanoes running all the way up to the northwest of the Pacific Ocean. The rest of the Hawaiian Ridge and the Emperor Seamounts are the extinct islands of Hawaii that have already been eroded beneath the waves. So this kind of gives you a little bit of an idea of the power of these mantle plumes outside of just creating plate tectonics. The smaller ones, what we think of as the smaller ones, can actually create volcanic islands. So the very last thing that we're going to talk about today are mountain belts. This actually is covered in a separate chapter in your textbook, but it goes along pretty nicely with everything that we've been talking about today. Because, of course, as we already know, mountain belts are formed through the convergence of either oceanic crust and continental crust, converging together, one subducting underneath the other, or more often, the collision between two continental pieces of crust and the resultant deformation that takes place to allow for the uplift of that crust. So we're going to look at all of these different steps in the evolution of mountain belts. But just know, to start us off with, that essentially all major mountain belts on Earth are formed because of convergence. They're intrinsically tied into the plate tectonic cycle. Now, the first step in the evolution of mountain belts involves the actual collision between two plates. Let's think about it, just for now, as the collision between two pieces of continental crust. As two pieces of continental crust move towards each other and then finally meet, you don't have the situation where either one of these plates can actually subduct beneath the other. So neither actually wins. It's kind of like a head-on collision between two 18-wheelers on the interstate. Neither is going to really win this fight, but there's going to be an extensive amount of deformation taking place as they both crumple as they move towards each other. Now, this crumpling that takes place is actually going to take place extremely slowly. Again, because these plates are actually moving at the rate in which your fingernails grow, 2.5 centimeters or 1 inch a year. But over time, faults are going to form and folds are going to form to accommodate all of the stress that is created when these plates converge. So when we talked about this in terms of geologic structures in the second lecture, we had a name for this particular type of stress. This is a compressional stress, a stress created when you take two things and push them together or push on material. Now, the more direct, convergent, or compressional stress you have, the lower the angle of the faults that form here are going to be, because that's going to allow the most crumpling of the material to take place if those faults are at a really low angle. And we call low-angle faults that can accommodate compression, we call those thrust faults. So one block of material actually ends up physically on top of the other block, or thrust on top of the other block. And so then you can take 100, 200, 300 miles of the Earth's crust and crumple it all up to only maybe be 50 miles across through the formation of all of these faults. Now, that's only going to be where you have brittle deformation. That's going to be closer to the Earth's surface. Deeper down, you have ductile deformation taking place. You have the temperatures and pressures necessary for this rock to essentially act like silly putty. And we saw what happens to silly putty when you apply a compressional stress. You fold the material. So the deformation that takes place when these continents converge are going to be thrust faults and folds. So we call these fold and thrust belts. This is the first step in the evolution of mountains, is all of this deformation of the crust. The first thing that has to happen is not the building of the mountains themselves. It's all of the thickening of the crust that occurs when you take 200 or 300 miles of crust and crumple it all together and make it a lot less wide when you shorten the Earth's crust. Now, by thickening the Earth's crust, by shortening it, by creating all of these thrust faults and all of these fold belts, you're going to allow the second step of the evolution of the mountain belts to take place. And this is going to be the part that actually allows for the most vertical uplift, the building of the mountains themselves. Because all of this crust is now thicker, that means it actually has to float up higher on the mantle than it originally did. It's kind of like the difference between how high a canoe can float up on top of the ocean versus how high a cruise ship can float up on top of the ocean. Because this cruise ship is larger and more massive, but also very buoyant, it actually ends up floating up higher. So the same thing happens to this thicker crust associated with the mountain building. First, the compressional stress creates all of these faults and folds and thickens up the crust and causes it to become shorter and shorter. And then all of this is going to rise up on top of the mantle. Now, the geologic structures that allow for this direct vertical uplift to occur are fundamentally completely different than the structures that allowed for all of the compression to occur. These are going to be mainly normal faults that you would think would actually accommodate extension, but the angle of these faults are so high that mostly you're just going to have this uplift occurring along the faults. So these block faults, creating these Horst and Graben structures, that's going to be really representative of the second phase of mountain building, where the material is actually going to float up higher on the mantle than it originally did. So I call this step the uplift/isostasy step. Isostasy, iso meaning equal, is just basically going to mean that given the same amount of crust but making it thicker, it has to then float up higher on the mantle. It has to balance, essentially. Now, the next step is the one that takes perhaps the longest amount of time. It might take 50 million years for the mountains to form in the first place, but it takes hundreds of millions of years to erode the mountains away. And this is even taking into consideration that you erode all of this mountainous material fairly rapidly when you compare it to the rate of erosion of low-lying areas. Even so, it still takes hundreds of millions of years to completely erode those mountains away to nothing. So all of the major mountain belts that we see on Earth today are consistently being actively eroded. Glacial activity and rivers and rain and wind and all of these forces are bringing down the mountains. And over time, that isostasy process reverses itself. So where you did have to thicken up the crust to make it float up higher on the mantle, whenever you erode down the crust, this balances itself out with the thickness of the crust underneath. And then slowly, you bring down the mountains. So really, any continental crust on Earth today has been through this whole cycle already. This is essentially how you create continental crust. You create these mountains, and then these mountains erode away, and what's left is the stable cores of the continents, or this material that we refer to as the cratons. So we have two major places in North America where you see mountain belts today. And so I'm just going to do a little bit of a compare and contrast between these two mountain belts, and you'll be able to get a little bit of an idea of how these three phases in the evolution of mountain belts have really worked upon these areas. The oldest mountain belts in North America are the Appalachian Mountains and all of the associated mountains along the eastern edge of North America. These are ancient mountains. These are depending on where you define the formation of these mountains occurring, they're between 250 and 350 million years old. So let's take an average of they're 300 million years old. You can get an idea that these were at some point far higher, far more massive mountains than they are today. 300 million years ago, when these mountains were newly formed, they would have rivaled the Himalayan mountains and Mount Everest. They would have been higher than 20,000 feet in elevation above sea level. So between maybe like 20 and 25,000 feet above sea level. Now, the highest peaks in the Appalachian Mountains are only in the range of maybe 6,000 feet high. So it's kind of like if you take my entire height and you eroded everything away down to, like, let's say my knees, and down from my knees to my feet, that was the only thing left. That's kind of analogous to what we're seeing with the Appalachian Mountains, that most of those mountains have eroded away, and we are really just seeing the very, very base of those mountains left behind. Comparatively, in the western part of North America, these are somewhat newer mountains. So these would be things like the Olympic Range, the Sierra Nevada mountains, the Rockies, including the Front Range and the Sangre de Cristo Mountains. All the mountains in the western part of North America all formed roughly around 65 million years ago in an event called the Laramide orogeny. So this isn't associated with continental convergence. This all happened as a result of pieces of the Pacific plate subducting at a low angle underneath North America and creating this uplift. So these mountains were never as impressive as the Appalachian Mountains were at their highest point. But you still have places like Pikes Peak at 14,000 feet. You still have some impressive high points along the Rockies and along the mountains in the western part of North America that we refer to as the North American Cordillera. So these mountains were never as high as the Appalachian Mountains, but they're higher today still only because they're younger. So it's going to be the youngest features on Earth that are going to be the most extreme. The deepest canyons and the highest mountains are only going to be the youngest features, those who haven't been eroded into obscurity, basically. So this would be a great opportunity for us to stop, and we're going to take a little field trip so that you can see some of these mountains for yourself. So I hope you enjoy it. So today, the field trip is going to take us to a place where I've actually taken students to personally. I often get a chance to teach through the LSU Geology Field Camp near Colorado Springs, Colorado. It's located in the Front Range of the Rocky Mountains. And one of my favorite places to bring students is to the summit of Pikes Peak. So you can go from the city of Colorado Springs and be at the top of Pikes Peak in under an hour. The elevation of Pikes Peak is 14,115 feet, and at the top, you have only one rock type. You have what's called the Pikes Peak granite. It's a potassium-rich, so very, very salmon-y pink granite. What you really get in these high places of the world, up at the tops of these mountains, is often really just granite and what we think of as basement rocks. So these are rocks that have formed deep in the crust and have actually been thrust upwards as these mountains by mountain building events. And this particular mountain building event was called the Laramide orogeny, and it occurred 65 million years ago. So at these really high places of the world where temperatures get very, very cold and stay very cold, you get much faster rates of erosion than you do at lower elevations, sometimes up to 10 times faster rates of erosion than lower elevations. So this contrast that we see in the United States between the Rocky Mountains and places like Pikes Peak with very high elevations and the smaller mountains of the eastern part of North America, the Appalachian Mountains, is really just a contrast between a much younger mountain building event of the Laramide orogeny that created the Rocky Mountains 65 million years ago to the much older mountain building events. There were several that actually created the Appalachian Mountains over 300 million years ago. So this is a beautiful place. I hope you all get a chance to actually see this in real life and not just virtually. Until next time, keep rocking.